Okay, in this video we're going to talk about hybridization. That is the mixing of atomic orbitals in an atom to generate a new set of orbitals that we call hybrid orbitals. And this is how we use to explain chemical bonds and bonding. So we have to remember in most organic molecules we have access to s orbitals and p orbitals, and there's 3 p orbitals depending on their orientation in space: px, py, and then pz. These orbitals can be combined in 3 different ways. The first way is to combine all of the orbitals. So if I combine the s orbital with the 3 p orbitals, I start with 4 orbitals. When I combine them together, I get out 4 new orbitals. And these orbitals are called sp3 orbitals. So when I combine 1s and 3p orbitals, I get an sp3 orbital. And you can see the shape of the orbital changes. One end has more electron density than the other, and there's 4 of these with 4 orientations in 3D space. These orbitals overlap with each other to form a tetrahedral geometry, as we can see here. One important thing to notice is when these overlap, every single bond angle we have here is 109.5. And this hybridization puts all of these orbitals as far away from each other as possible, and that gets you a bond angle of 109.5 degrees. Looking at a couple examples at the bottom of the page, if we take the molecule methane here, a carbon atom with 4 hydrogens, this has a hybridization of sp3. And there's a couple ways to think about hybridization. We can use the AXE model, where A is used to describe the central atom, X is the atoms around it, and then E is the number of lone pairs. So in this example of methane, this would correspond to a structure of AX4, where A is the central atom carbon and it is surrounded by 4 hydrogen atoms, X4. So there are 4 atoms around it, which requires 4 bonds. To get those 4 different bonds, we need 4 orbitals, 1s and 3 p's. So this molecule is sp3 hybridized. If we look at the next example here of ammonia, here we see a nitrogen atom surrounded by 3 hydrogen atoms and a lone pair. And what we have to remember when we're talking about hybridization, the lone pair counts. That lone pair has to go into an orbital. So in this model, we would call this AX3E because we have 3 hydrogen atoms around it. That's the X3, and the E stands for 1 lone pair. When we're looking at the hybridization, we want to look at the total number of things surrounding it. So here we have 4 hydrogen atoms. Here we have 3 hydrogen atoms and a lone pair. So together, these add up to 4 separate things. To accommodate all of those electrons, again, the nitrogen atom has to be hybridized for sp3 to provide 4 orbitals. So what we have to keep in mind here is we're always going to look at the number of atoms around it and include the number of electrons to figure out our hybridization. So let's take a look at our next example here. Now we're going to talk about sp2 hybridization. So again, we always have access to 1s and a total of 3 p orbitals. So in this example, we have an s orbital, 2 p orbitals, px and py, and then we have this pz. Here we're simply going to combine the s and 2 of the p orbitals. And when we do that, we combine these 3 orbitals s and two p's, and that produces us with what we call an sp2 orbital. And again, because we started with 3 orbitals, we get out 3 sp2 orbitals. These 3 sp2 orbitals are oriented in space, so the electrons are far away from each other as possible. And when they're combined, we see here, we have a bond angle now of 120 degrees. And that puts these orbitals and these electrons that are repelling each other as far away from each other as possible. What we have to keep in mind is we used an S and 3 P's, so we have this PZ left over, and here's this P left over. So when we look at this for an example, here we're going to look at a molecule of ethylene. We see we have a carbon that's connected to a hydrogen, and then another carbon. Now this carbon is connected by a double bond here, but it's only connected to one thing. So if we go back to our AXE model, looking at that atom, we say our central atom A is our carbon, and it's surrounded by 3 things. So that's AX3, meaning a hydrogen, and a carbon atom. So that's AX3. Because that central carbon atom is surrounded by 3 things, we therefore know that this is now sp2 hybridized, and that all of the bond angles we see here, and there, and there, in orange, are all 120 degrees. Okay, and that's obviously the same for the carbon on the other side because it's symmetric. So what we have to keep in mind is what happens with this extra p orbital here. Well, that p orbital still exists on this carbon atom, so I'm going to draw that in here, and obviously there's another one on the other side. Now these p orbitals can also participate in a bond. So if we look here, these p orbitals can participate in a bond, and this is now a different type of bond. So when orbitals are parallel to the bond, that's called a sigma bond. So this bond in blue is a sigma bond, that bond in blue is a sigma bond, and one of the bonds of a double bond is a sigma bond. So those are called sigma bonds. And what we see here is the orbital is in the same direction as the bond. Here and here, there and there, and there and there. But now we have another bond that's formed. This p orbital here and that p orbital can share electrons. And that type of bond in green is called a pi bond. And a pi bond exists when the orbital is orthogonal or 90 degrees to the bond. So that's what a pi bond is. And pi bonds have less orbital overlap, so they are weaker. So we see our p orbital is straight up and down in both cases, and the bond is 90 degrees to the direction of that orbital. That's what it means being orthogonal. So what we see when we have a double bond in this system here, so let's redraw this. Single bonds are always sigma bonds, but a double bond actually consists of one sigma bond, and that sigma bond is shown here, and then also one pi bond. Pi bonds are always made of the orbital overlap of two p orbitals. Alright, so let's write that down, just a couple notes to remember. Sigma bonds are stronger than pi bonds. Alright, so that is one note we want to remember. Sigma bonds are stronger than pi bonds. And let's write this on the other side here. That pi bonds are formed from the overlap from two p orbitals. Okay, so double bonds will consist of one sigma bond and then one pi bond. One sigma bond and one pi bond. So let's look at our last example of hybridization. In this case, we're now looking at sp hybridization. So again, we have one s orbital and three p orbitals, px, py, and pz. Now we're going to combine just two orbitals, one s and one p. So these can now combine to form two sp orbitals. Two orbitals in, two orbitals out. And again, the shape of these change a little bit. And we have two of these. So of course we have left over two p orbitals, one pz and one py. So when we overlap our hybridized orbitals here, we now see that the orbitals are in complete opposite directions of each other. So around the center of an sp hybridized orbital, our bond angles are now 180 degrees. So if we look at our molecule acetylene here, we look at our carbon atom. This carbon atom here, again we can use our AX model, is attached to one hydrogen and one carbon. So this is AX2. And therefore, because this is AX2, we only need two orbitals for this central hybridization, and therefore the hybridization of this carbon is sp hybridized. And what we know is the bond angle from the H to the carbon to the other carbon of the triple bond is 180 degrees. Now looking at this a little bit different, here we've taken this apart. Here's our carbon atom. There's an sp hybridized orbital to the left, an sp hybridized orbital to the right. Same on the other side. When these combine, one sp hybridized orbital forms a bond to the 1s orbital of the hydrogen. The other sp hybridized orbital forms the sigma bond to the sp hybridized orbital of the other carbon. Okay, so that's in here. So let's just try to show that a little bit. So there's our one sp, there's our other sp. And again, we have now two p orbitals left over. One up and down, and one perpendicular to the plane. And you can see those here. Here's the one perpendicular to the plane and the one up and down. So the center bond we see in blue is a sigma bond, direct overlap, and now we have two pi bonds. The one up and down forms a pi bond here, and the one in and out of the plane forms a pi bond there. So when we have a triple bond, you have one sigma bond from the two sp hybridized orbitals, and now we have two pi bonds that come from the two p orbitals that are left over. So we always look at the central atom to figure out the hybridization, and that will tell us our bond angles. Okay, so a couple of notes to consider. Most organic molecules are really going to contain carbon, nitrogen, oxygen, hydrogen, and X, where X stands for halogens. First, let's talk about carbon, nitrogen, and oxygen. And halogens will usually follow this. Carbon, nitrogen, and oxygen will have hybridized bonds consisting of s and p orbitals. So the options here are sp3, sp2, or sp. Alright, these atoms have to be sp3, sp2, or sp hybridized, and halogens will usually follow that pattern, usually being sp3 hybridized. Why is that? Carbon, nitrogen, and oxygen are in row 2 or period 2 on the periodic table. That means they only have access to s and p orbitals. If you remember studying quantum mechanics, the principal quantum number, n equals 2, carbon, nitrogen, oxygen are in row 2, so n equals 2, that's the principal quantum number. And then we have the second quantum number, or the orbital quantum number, is L. So when n equals 2, L can only be equal to 1 or 0. L is a p orbital, and 0 is an s orbital. So these atoms, being in row 2, only have access to p orbitals and s orbitals. Therefore, they can only be sp3, sp2, or sp hybridized. Carbon, nitrogen, and oxygen can never have an extended octet. They can never make 5 bonds. If we remember about hydrogen, hydrogen is in row 1 or period 1, and it cannot hybridize. It only has access to s orbitals, where L is equal to 0. So it just has one s orbital. It will never hybridize. Occasionally we'll see examples where atoms do have extended octet, and again, that's not as common for most organic molecules. But elements in rows 3 or higher, periods 3, 4, 5, and beyond, have access to d orbitals. Therefore, they can have an extended octet. So if we think about something like PCl5, here we have a phosphorus atom surrounded by 5 chlorine atoms, and we have to have 5 hybridized orbitals to make those bonds from the phosphorus to the chlorine atoms. So therefore, the hybridization of this phosphorus has to be sp3d. There's only one s orbital, 3 p orbitals, so we have to have another orbital to hybridize. So the central phosphorus atom is sp3d hybridized, and there are 5 sp3d hybridized orbitals. And that's not something that we really see as common when we're talking about organic molecules, again, because typically we're looking at carbon, nitrogen, and oxygen, and then hydrogen, which doesn't hybridize. All right, so let's take a look at an example here and kind of work through a problem together. What I want to do is just think about what's the hybridization of every atom we see here. And remember, hydrogen can't hybridize, so this hydrogen forms bond from a 1s orbital, 1s, s orbital, and s orbitals here. So we're really focusing on the carbons, oxygens, and nitrogens. Okay, looking at our first carbon atom, we see that this carbon atom here is attached to 3 hydrogens, and then a carbon. So that carbon is making 4 bonds. So if we think of our AXE system, this would be AX4. There are 4 atoms around it, 3 hydrogens and a carbon. A total of 4 things around it. Therefore, this carbon atom would be sp3 hybridized, and there are 4 sp3 hybridized orbitals around that carbon. Looking at our next carbon atom, here we have a carbon atom attached to another carbon atom, a hydrogen atom, and then attached to another carbon atom through a double bond. Again, using this AXE system, the central atom A is the carbon, and X is the atoms surround it. There are 3 atoms, hydrogen, carbon, and carbon. So this is AX3. So what we need to do here is recognize that we have to have 3 orbitals. Those 3 orbitals are made from 1 s and 2 p's. Therefore, that carbon atom is sp2 hybridized. The extra p left over is used to make that double bond. And again, we can clearly see that this carbon next to it again is attached to an H, a carbon by a double bond, and a carbon. That's 3 separate things. So again, that's AX3, and it is also sp2 hybridized. When we look at our next carbon atom here, this carbon atom is attached to a carbon, another carbon, and an O through a double bond. Again, that's 3 separate things. So this is also sp2 hybridized. Looking at our oxygen, now we have to remember that oxygen will have lone pairs, and lone pairs go into orbitals. So we need to draw in our lone pair, and oxygen makes 2 bonds and has 2 lone pairs. So we have to remember that those lone pairs count when we're talking about hybridization. So when we look at this oxygen in our AXE model, the oxygen is A. It's attached to 1 atom, carbon, so it's AX, and that oxygen has 2 lone pairs, so that's AXE2. Again, thinking about the hybridization, there are a total of 3 things, atoms and lone pairs surrounding it, so we need 3 molecular hybridized orbitals to do that. So again, what that means is that this oxygen atom is sp2 hybridized, and there are 3 sp2 hybridized. So an sp2 hybridized orbital from the oxygen to the carbon, lone pairs in one of the sp2 hybridized orbitals, and the other lone pairs in an sp2 hybridized orbital. When we get to our next example, here our carbon atom, that's attached to 4 different atoms, a carbon, a hydrogen, and a nitrogen. That follows this AX4 model here. So we clearly see that this carbon atom here is sp3 hybridized. And again, we have 4 sp3 hybridized orbitals. One from the carbon to the H, one from the carbon to the H, carbon to carbon, carbon to nitrogen. Looking at our nitrogen, again we need to remember that the nitrogen will also have a lone pair. So if we look at our model here, the central atom nitrogen we call A. It is attached to 2 hydrogens and a carbon, so that's 3 atoms, AX3. And then our nitrogen has a lone pair, so that is AX3E. Again, that gets us 4 things surrounding that atom. We need 4 hybridized orbitals. Therefore, the hybridization of that nitrogen is sp3. Another thing I'd like to do is count our sigma bonds and go through our sigma bonds and our pi bonds. So if we look at our first atom, this first carbon, it has 4 bonds, so there's a sigma bond to these 3 hydrogens, 1, 2, 3, and 4. So these are all sigma bonds. And including in that sigma bond is this sigma bond here. Looking at our next carbon atom, this carbon atom has 1 sigma bond, 2, 3. So there's a total of 3 sigma bonds there. Remember, a double bond consists of 1 sigma bond and 1 pi bond. So this has 1 sigma, and then in green we have a pi bond. That is made from the p orbitals that were left over in the hybridization. Same for the following carbon. 1 sigma, 2 sigma, 3 sigma, and again this pi bond in the other direction. Looking at our next carbon, we have 1 sigma, we already counted, another sigma bond, and another sigma bond there. Again, we have all of our single bonds are sigma. Our double bond has 1 sigma and 1 pi. As we continue on, again, this next carbon here has 1, 2, 3, 4 sigma bonds in blue. The nitrogen, I'm just going to draw them out, 2 sigma bonds to the hydrogen, and then it has the lone pair. So if we look at this molecule in its entirety, we have everything is a sigma bond except for in green, and we have 2 pi bonds shown here. Thinking about bond angles, we always look at this central atom. If this carbon is sp3 hybridized, all of my bond angles around here are approximately 109.5. This central carbon here is sp2 hybridized, therefore these bond angles are all 120. This carbon has sp2 hybridized, all of these bond angles are approximately 120. Again, every bond angle around the carbon and from the oxygen lone pairs to the carbon are approximately 120. Again, because this is sp3 hybridized, every bond angle here is 109.5, and same for the nitrogen. So that's really one way to figure out hybridization of atoms in a molecule. I want to show you another way to kind of think about this, so I'm just going to erase everything here real quickly and think about this a different way. And now what we're going to do is remember the fact that carbon atoms, oxygen atoms, and nitrogen atoms can only be sp3, sp2, or sp hybridized. Okay? And what we really want to think about is now double bonds or triple bonds. Okay? When we think about a double bond, we know that a double bond consists of 1 sigma and 1 pi, and that's true for all the double bonds we have. We have 1 sigma and 1 pi. So looking at this, if we remember that a pi bond has to be made from 2 p orbitals, those p orbitals are not part of the hybridized atom. So when I look at this carbon atom, there's no double or triple bonds here. Therefore, every orbital, the s and the 3 p's, participate in the hybridization. So another way to look at this is just to count the number of double or triple bonds you see. This carbon has no double or triple bonds, therefore it's sp3 hybridized. This carbon here has a double bond. One's a sigma, one's a pi. The pi comes from a p orbital. So that p orbital is left out of the hybridization process. If I have one s orbital and three p's, but one of them's left out, that means that this carbon atom has to be sp2 hybridized, because I've used two of the p orbitals for the hybridization. The other p orbital makes the double bond. This carbon has one double bond, so it's sp2 hybridized. Same with this carbon, because it has a double bond. Same with that carbon, because it has a double bond. And same with the oxygen. So I'm kind of thinking about this in the opposite way. If something has a double bond associated with it, that's one pi bond, and that means that you need one p orbital to do that. So when you take away one p orbital, you're left with a hybridization of sp2. So all of these atoms are sp2 hybridized, and therefore all of the bond angles around these are 120 degrees. When I look at my next carbon here, it's not participating in any double bonds. Therefore, we know that this carbon is all of the orbitals, the s's and the p's are participating, so that's sp3 hybridized, and same with this nitrogen. This nitrogen has no double bonds, it has no pi bonds, therefore all of the orbitals are participating in the hybridization, and that's sp3. So that's another way to think about hybridization. So what I want you to do is to go through and label the hybridization of every atom of this second structure. I'm just going to remind you again that nitrogen has one lone pair, and that halogens form one bond and have three lone pairs. And what you can do is do the hybridization of every atom, the chlorine, the carbon, and all the carbons and the nitrogen. Obviously the hydrogens don't hybridize, so we won't have to do that. And then what I'd like you to do is give me a couple of bond angles. So the bond angle from the chlorine to the carbon, we'll call that bond angle A. Give me the bond angle here, we'll call that B. So that's from this carbon through that carbon there. And then the bond angle here, we'll call that C. That's from the hydrogen to the carbon to the nitrogen. And again, to figure out the bond angles, you simply look at the hybridization of the central atom. So for A, you look at the hybridization here, B, the hybridization there, C, the hybridization there. So for this problem, give me the hybridization of the chlorine, all of the carbons, and the nitrogen, and then the three bond angles A, B, and C.